Welcome to geometry class. Today we need to talk about altitudes in triangles. Altitudes in triangles. Most of us are familiar with the word altitude. We think about plains, we think about mountains, and we're asking the question, how high am I above the ground? Or perhaps more particularly, how high am I above sea level? In geometry, the word is closely associated with that idea, but we do need to draw some distinctions. First, for a definition, an altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. So let's look at some obvious examples, and then we'll look at some that are slightly less obvious. Here's triangle ABC, and if I asked you to identify the altitude to vertex A, well, we know it's the perpendicular segment from A to line BC, or the line containing BC, and so we're talking here about just this segment here. We'll call that AD. Okay, AD. So AD is the altitude with respect to vertex A. Here's an obtuse triangle. I've only labeled one vertex. Suppose we want to identify the altitude to vertex A again. Same thing. It's just this segment right here. That's the altitude. Notice it carries a similar connotation in this diagram as it would in real life. It's the height of A above sort of the ground here. The problem we run into in geometry is that there is no up, right, left, down, any sort of direction in that sense, no absolute direction. So if I were to turn this diagram upside down, or sideways perhaps, talk about this triangle with vertex A here, and I asked about the altitude to vertex A, it would now be here. Perpendicular segment from the vertex to the line containing the opposite side. So we find already that there's this distinction in geometry that altitudes are not necessarily measured from the ground up, so to speak, but always measured rather from a vertex to the line containing the opposite side. Now we notice this language here, to the line containing the opposite side, and it's worth asking the question, why not just say that an altitude is the segment from a vertex to the opposite side? Why the line containing the opposite side? Why that additional language? Is that just extra language? The answer is no. Let's take a look at this situation here. Suppose we had this triangle. It's also an obtuse triangle. Suppose we needed to know the altitude not of vertex A, but the altitude relative to vertex C. Suppose we wanted that instead. A is easy. A lies right in here. We all know where that is. We've looked at that already. But what about the altitude to vertex C? Well, we know that the altitude is the perpendicular segment from C to the line containing AB. That line containing AB can be extended out this way. And so we find that the altitude to C actually lies here. It actually lies outside the triangle, and it never intersects segment AB, but it does intersect line AB. So that's why this additional language when we talk about the line containing the opposite side. In fact, you'll find anytime you're dealing with an obtuse triangle, two of the altitudes will lie outside the triangle. Notice, and this is perhaps inferred in things I've already said, notice that every triangle has three altitudes. Let me just start with an acute triangle. We'll take a quick look at that. Here's an acute triangle. We'll call it ABC. So those seem to be the default letters. And the altitude to A would be here. Altitude to B is here. And the altitude to C, of course, would be right here. Notice again, every triangle has three altitudes. Doesn't matter if it's obtuse, right, acute, makes no difference whatsoever. An altitude, as I've already said, can be inside a triangle, can be outside a triangle, could also be the side of a triangle. Let's take a look at that. How could an altitude be the side of a triangle? Let's take a look at this triangle. It's a right triangle. And let's look at the altitude to vertex A. Remember, an altitude is a line segment which goes from a vertex to the line and is perpendicular to the line containing the opposite side. So side BC is opposite to vertex A. Therefore, the altitude here is this segment, AB, because that is the segment that is perpendicular to BC and ends at A. So we find here that side AB is actually the altitude to point A. Side BC is the altitude to point C, and we'd find that the altitude to B is in here someplace. So, sometimes, again, we find that the altitudes are inside the triangle, sometimes they're actually the side of the triangle, sometimes they're on the outside. There's a very straightforward way of figuring out where they happen to be. If it's acute, if the triangle's acute, then all three altitudes will be inside. If it's a right triangle, then two of the altitudes will be sides themselves, and if it's obtuse, then two of the altitudes will lie outside. You may have noticed as I was doing some of these constructions, you may have noticed and picked up on the fourth point of concurrency here. Altitude, altitude, altitude. There's our fourth point of concurrency right there. It's called the orthocenter. The orthocenter theorem says that the lines that contain the altitudes of a triangle are concurrent at a point. Let me fix that. Are concurrent, that's redundant. The lines that contain the altitudes of a triangle are concurrent at a point called the orthocenter. Let's look at the construction. In order to construct the orthocenter, we first have to construct the three altitudes. To do that, we'll just start with a random triangle here. And it will be an acute triangle. There we go. And to begin with, we simply have to construct the perpendicular lines through a point, where the point referenced is each of the vertices, one in turn, and then the line has to be perpendicular to the opposite side. So we're going to start at vertex A, and we want to construct a line that is perpendicular to BC, that is segment BC, but passes through A. So to do that, I will place the compass at A, and we'll set it so that it will intersect BC in 2 points. This is a fairly decent setting here. There's 1, 2 points. Notice that as I do that, it has nothing to do with these two sides here. These two sides are irrelevant when I'm trying to construct a line perpendicular to BC that passes through A. I'm only focusing on A and this side down here, BC. Once I've found these 2 points, I'll now put the needle of my compass on one of them and swing an arc, and then move it to the other one here and cross that first arc. That point will be where my perpendicular line will pass through, like this, and the altitude lies there. The altitude goes only from the vertex to the opposite side. But I'm going to go ahead and draw the whole thing in, just so that it's clear where that construction came from with respect to this point down here. So that's the first line containing the first altitude. Now we'll repeat the process at vertex C, and when I do so, my only concern is with respect to side AB on the other side over here. You'll notice that as I drew this arc over here, it missed segment AB. In order to construct the altitude correctly, I'm going to extend side AB so that it actually intersects that second arc I made. Now I have 2 points of intersection, one here closer to A, and one over here, which is closer to B, but is actually outside or past point B. Again, I'll move my compass to one of the intersections and make an arc, and then to the other intersection and make an arc, and I will connect that intersection with vertex C, from C to the intersection down this end. My altitude lies between vertex C and the opposite side, and this line is my line containing my altitude. Finally, we need to construct the altitude to vertex B. So I'll put my compass at point B, and again swing an arc, swing a second arc. You can see that those arcs just caught the lines, that is the segment AC, just short of C and just short of A. And so we'll be able to use those just fine. I now put the needle of my compass at the first intersection and draw an arc. Switch it to the second intersection and draw an arc. I then connect those two arcs, the intersection of those two arcs, to vertex B, and there we have the line containing altitude to point B. Again, the altitude goes only from B to the opposite side. Each of these, we can be sure now, are perpendicular, and the orthocenter lies there, the point of concurrency where the three of them meet. And that is the construction of the orthocenter, having constructed one by one the three altitudes of the triangle. That was the construction of the altitudes in the triangle, which will always identify for us the orthocenter. I recommend that you try to work through some problems, try to construct the Orthocenter. It may be particularly helpful to do an acute triangle, a right triangle, and one obtuse triangle just to make sure you can see where those all line up. If you have any questions, send me an email.